All right, now we're doing 2.2 for math. Um, this is called linear inequalities. Inequalities are something like less than, greater than, less than or equal to, greater than or equal to, or just not equal to. Um, so just going over them, we have less than, greater than, less than or equal to, greater than or equal to, or not equal to. Excuse me. That's what we're going to be using through this chapter. Things to know. Um, you have intervals and endpoints and unbounded intervals. So if you look at let's just go straight to drawing a chart here. If you look at this chart, we have 0, 1, 2, 3, take ever, -1, -2, -3, taking forever, -5. Okay, you know what? I'm gonna make this easy on myself. I'm gonna copy it. All right. So this inequality, let's say we had something like x greater than 3. We would draw a circle. So there's something to know here, and this is, let me show you that this is a circle, right? An open circle is not shaded in, and greater than 3 is this way. Excuse me. So this circle has to do with these. Um, I'll just draw it right here. This circle, when it's like this, has to do with those. Okay. Um, Not equal to also is just a circle. So these and this are together, and then these have a closed circle. All right. Uh, let's look at another one. It will be x less than or equal to -2. Now we see -2 on the chart here. And we know now that if it's less than or equal to, it will be a closed end dot. So let's draw that. And if x is less than or equal to -2, our line goes this way. And we draw an arrow because it's unbounded. Unbounded means you're drawing it and you're putting an arrow on it and it goes on forever down this line. So -6, -7, -7, -8, -1 billion, -1 trillion, whatever. It just goes on forever that way. All right. So these are singular inequalities. Now we're going to do compound linear inequalities. Um, so let me just, I'll leave that up there as a reference. So compound inequalities are not as complicated as they sound. Um, so if we have something like a -1 less than x less than 3, the -1 would have a circle on it, not filled in because it's one of these. Somebody knocked on my door. I wonder who that was, Ben. All right, so -1 And then we have x, and then negative. Oh, sorry, 3. So we have open dot on 3. Now, where do the arrows go? Or are there arrows? Well, this is a bounded interval, which means x only exists between -1, less than -1, or less than 3. So x would represent this area here. And I'm doing it like this so it shows it better. So it's not equal to -1, but it's anything in between -1 and 3, but not equal to 3 because these don't have little equal signs under them. Okay, so that is a compound linear inequality. Let's do a couple more. Oh, my handy dandy little thing here. So okay, this one is a 0 less than or equal to x, which is less than or equal to 4. Now we know we see x. I mean, we do see x, but we see 0, and 0 is less than or equal to. Less than or equal to uses the closed in, so we will close in a dot right here. This one is less than or equal to 4, so we will close in a dot right here. X is in between, so it will be this area right here. Okay. And then they can be mixed. Just to show you, they can be mixed like -5 less than or equal to x less than 4. So less than or equal to is a closed in dot at -5. And less than is 4 is just an open dot because we have it up here. And x is everything in between. So this area right here. Okay. All right. So there's something called interval notation, which takes those compound ones we just did and changes it to interval notation. It also takes the simple ones too. So remember, we have the open here and the closed here. We can write these in interval notations. Let me see if I can do these. Yeah, let's just start with this. X is less than. Let's just give it another variable k. And this is in your book. The interval notation for this, because it's a less than and it's open, is just parentheses, negative, infinity, k. Okay, so x goes to infinity. Like whenever I said that, on this graph, if we filled in, let's say k was, let's just do a real world example instead of using the stupid variables. All right. Let's say k, let's say this is 1, just regular old 1. We would have drew an open circle and then said this goes this way forever. Infinity means forever. So it goes to the negative, these are negative, goes toward negative forever, and then 1. Stops at 1, starts at 1, whatever you want to think of that as. That's notation for that. So there's notation for different types. So let's look at this scenario, this one would just be 1 on this side because, and this goes to infinity this way. That's an awesome infinity symbol. But less than, and on these single ones, less than the infinity symbol is on the left hand side, greater than the infinity symbol is on the right hand side. There's also these x less than or equal to 2. I just arbitrarily chose 2. This guy is a little different. So we know that negative infinity is one of them, and we know 1 is one of them, right? But this time we put a different bracket here because this is less than or equal to. Remember how we use this closed dot to show that? We're also going to use this bracket to show that when we're doing interval notation, that's what this is. These are interval notations. Interval notations. And we'll just show this one 2. If it's greater than, what do you think we do? Should we just reverse it? Yeah, we just reverse it. So we would say 2 over here and then infinity over here. And that would be interval notation for that. Okay. Now, I want to go over the more complex interval notations. It's actually not that complex. So let's say we had -2 is less than x, it's less than 3. The way we would write that in interval notation is just -2, 3. Notice they're open. I mean, they're the open symbol, they're brackets like that. And these are the open right here. All right. And notice the order too. So this one starts at -2 and then the 3 because these are less than symbols. Let's get into a little bit different. And usually they're always less than this way. If it's not, we may need to do some simplification. That'll come later. Usually you always want it in this way so you can write it in notation this way. Let's look at the closed. Let's just show them the same numbers, less than or equal to. Let's make it to 3. This time we use those other brackets for both sides, because both have less than or equal to. Now, you can also have mixed, and I think we've seen some of that, but if I had -2x, oh, well, they gotta be a mix, so let's mix them up. And this would be bracket -2 and then 3, but then the brace. Okay. Now, that will help you through this chapter, knowing those notations and applying those. So let's start applying them a little bit. So identify each inequality, and I'm reading the instructions for the example because you'll have something like this in your homework. So identify each inequality as bounded or unbounded and write it in interval notation. Okay, so they give you x is greater than -4. Is it bounded or unbounded? So let's go back and look at bounded and unbounded. And I think we went over it, but I want to make sure. Now, bounded Excuse me. Um, well, let's look at unbounded. Unbounded is an interval that continues infinitely in one or both directions on a number line. Bounded has a limited range of values, which are part of the solution. So, does this go? Oh, get my book in the right place again. Does this go out to infinity? Yeah, let's. I think you already know, but I'm gonna just. We have -4, and we're gonna open it, and x is greater than -4, so it goes out. Um, it's not bounded, so this is unbounded because it goes out. Oh my goodness. Okay, my writing is not that great on this machine. Unbounded because it goes out to infinity. That's the definition of unbounded. Let's write it in notation. So we have it is a greater than sign, right? So what did we do on greater than signs? What did we write first? We wrote the number first, off to infinity. And that's how you write that. So we said it was unbounded and we wrote the interval notation. Okay, let's continue on just for fun. Let's give a little more complex one. -2 is less than or equal to x, which is less than or equal to 10. Now, is this bounded or unbounded? Now, you can look at this and know it. We can see it because these closed or they're closed or bounded, and these are open or unbounded. So this has both closed, which means it's bounded. Now, write this in interval notation. If it's bounded, we write our little square bracket thingy. And this side's bounded too, so we write our square bracket notation thingy. And that's the notation. All right. Now, didn't this chapter say something about solving linear inequalities? We're getting there. Now, there is a property that you need to know about. And your book says stuff about the properties, but um, you know, it let me just point out the most important here. Let's say you're trying to solve something, right? And you're carrying over addition. So you'll have stuff like well, let's use variables right now. A plus B is lost it. A plus B is, well, let's say greater than C, something like that. So you'll have things like this. And if you want to move the B across, that's not a big deal. You'll move it across. And you get A is greater than C minus B. So that's not a big deal. You don't have to change anything. It's just like there was an equal sign right here and not an inequality. But if you wanted to do things like multiplying or dividing, it may be a little different. So A times C greater than B. Let's say we want to take the C and put it over to the other side. So let's divide the C out, and there you go. A is greater than B over C. Not a big deal, right? Well, this may be a big deal if this was a negative C. If this is a negative, if you're multiplying or dividing a negative across an inequality, you have to change the inequality. Here's what I mean. Divide the C out. This is multiplication. We divide the C out, the negative C. But we also have to change the way this moves. So this actually becomes A less than B over negative C. Yeah. Okay, so let's look at something like this. Okay, so we have x plus 1 is less than 3. Now, to solve this, it's fairly simple. I mean, we take the 1 from this side and take it on this side. So that gives us x less than 2. So to graph this, handy dandy graphing machine, we will write the 2 here and open dot, and then x goes this way, right? Well, there's another side to this too. Because it's an inequality and we solved for x, we also look at it as x equals 2. Remember those inequalities we solved? And we had to, last chapter, we had to split it, absolute values, split it in two. It's similar. That graph looks like this. We have 2, but we still put our dot on 2. So 2 is actually our critical number because it's a key point in the line. And what we're saying is going this way and we're going this way. And 2 is our number, which is to say negative infinity to 2 for this side, and 2 this side, 2 infinity on this side. It gives us 2 intervals. So a way we could look at that, and I'm gonna do this. We still have our x less than 2 that we solved, and our x equal to 2. We found out the notation for this is, well, negative infinity to 2, excuse me, and 2 to infinity. Now, we could write it this way. That would help. Because what we're going to do, we're going to start plugging in numbers and trying to check our work here. So, to see if there's a solution and which one's right or which one we should use. This may be easy for this, but later on, like in chapter 3, it's going to be harder to do this, and it's going to be more complex. So we need to have the basis for this down. Okay, so for this one, we have a test point. We want, okay, this is our intervals right here. Just going to take this out. This is our intervals. Okay. And that is supposed to be an A, you know what I mean. This is our test points. Test point. And this is our equation. Remember our original equation was x plus 1 less than 3. And is it a solution? Okay. So test points, you never use the critical number. You always use something outside the critical number. Our critical number in this case is 2, so we don't want to use that. Something easy to use is 0. So let's plug in 0. That's our test point. And so this would be 0 plus 1 less than 3. That's what we're trying to solve. Can we solve that? Well, let's find out. If we have 0 plus 1 less than 3, is we solve it, plus 1 less than 3. 0 just goes away, so we're actually left with 1 plus 1 is less than 3. Is that true? Is 1 less than 3? Yes. So there is a solution. For this test point, we need something inside the range. I forgot to mention that up here. 2. So, okay. We're choosing 2, in this case, 2, and something down the line here, which is why we chose 0. In this interval, we have 2 and something along the line this way. See, this is broken right here. This is the critical number, which is 2. So we want to choose something this way on the line. I choose 3, just because it's the next number in line and it's the smallest number. 3 plus 3 less than 3. That would be 6 is less than 3, and that is not true because 6 is not less than 3. So we know that there's no solution for this interval here. So now you can say that the solution to this interval is this negative infinity to 2. So you could graph that, this, and we have a solution going that way. And that's our solution. We know that this is not a solution, so the only solution is this guy. That's the answer. Okay. Let's solve some linear equations now. Now that you have all that information that we just gave you, let's actually solve some stuff. Now's the fun part. So, okay. 3, let's do it. No, I'm gonna like this. I write it right here. 3x plus 2 greater than 5. Now, to solve this, we have steps, and that's in your book, solving a linear inequality in one variable. We simplify each side of the inequality. Okay, well, it's already done. We isolate the variable term, just like solving with the equal sign here. So let's isolate the variable term. -2, -2, 3x greater than 3. Oh, that's a greater than sign? That looks horrible. All right. And now this is multiplication. We divide this out. It's not negative, so there's nothing we need to do. And we find that x is greater than 1. Excuse me. Okay. So now we need to graph the critical number, which is just right here. If we're graphing that critical number, we see it's 1, we just draw that. And it goes out this way and out this way. Now, this is where you write your interval. This will help you write your intervals. This is going out to infinity, so negative infinity. This is going to 1. And it's not equal to, so it is just a regular brace. This is a regular brace at 1 here, and it's going out to infinity. Now we need to test to see which one of these, or if both or none, are a solution. And an easy way to do that is to do it in that little chart form that I gave you a while ago. And it will help you keep organized. So I'm not going to write all the little things up above it. We know what we're doing, I think. So our test points here. Then we have our check here. And then is it a solution? So test point, we're going from 1 backwards. So let's pick the next one, which is a 0 on the line right here. So 0 is what we're going to pick. And the inequality was 3, 0 now, plus 2 greater than 5. Well, the 0 crosses out the 3, and that just leaves us with 2 greater than 5. Well, I don't think 2 is greater than 5, so nope solution. In this one, we have 1 going to infinity this way, so we'll just pick the next number to 2, and we will write this as 3, 2 plus 2 is greater than 5, looking like it might be a solution. 2 times 3 is 6. 6 plus 2 is greater than 5. And this is 8 is greater than 5. And yes, this is a solution. So if we wanted to graph that solution, and we are supposed to, running out of room. And it is this one. So we would start here, line this way, and this is our solution. Okay. Let me do some more. And I'm going to try to go ahead. I'm going to go ahead and delete the top parts. I think you got an understanding of that. And then we're going to go on with some more solutions here. Solutions and checks. So the next one is a 4 minus 5x greater than 24. Simplify each side. Well, it's already been done. It's simplified. Now we need to solve for x. All right, so to solve for x, let's pull this 4 over. Let's -4, and then -4. So this turned out to be -5x greater than 20. All right, so let's break up this multiplication. And look, we have a -5. Let's divide each side by -5. This now changes to be this because we carry that negative through multiplication or division across. So now this is x less than 20 divided by -5, which is just -4. Okay. Now I want you to graph the critical numbers. I mean, you can see it there. Graphing the critical numbers at this point is helpful because it will help you write your intervals. That's important to write your intervals correctly from this. So our critical number is -4 and it is open dot because this is not less than or equal to, it's just less than. And it goes both ways. So this way, the arrow, oof, bad arrow, and this way with the arrow. So this one is -infinity to -4. This one is -4 to infinity. That's our two intervals. Now we need to write those intervals down and test them. So -infinity, -4, horrible handwriting on this thing, and -4 and infinity. Our test points. Well, what shall we use for test points? Well, we get a -4, and we know this interval goes this way. So our next interval is -5. So let's try -5. So it would be 4 minus 5 times -5 is greater than 24. All right, to solve this, we got -5 times, well, let's just say 5 times -5, which is what? Well, -5 times negative, whatever. And it is 5 times 5, which is what? Come on. It's 25. So this would be positive. Oh, let me just do this to see. 5 greater than 24. Because it's important. So -5 times -5 is 4 plus 25. It's greater than 24. So this is actually 29 is greater than 24. And is 29 greater than 24? Yes. Yes, it is. And that's a horrible yes, but it says yes. Trust me. All right. Now, -4 and infinity. Let's pick an interval. So we're going this way. I'll tell you what, let's pick 0. If I had the opportunity to pick 0, it may be the best one. I don't know what the book chose, but looks like the book chose 1. We're choosing 0. 0 is easier to solve. So this is 4, -5, 0, greater than 24. So this actually ends up being 4 is greater than 24. Now, is 4 greater than 24? No, it's not. So that's not a solution. Not a solution. Now, let's graph our new solution. And it is -4 right here, open, and it goes backwards this way. And this is the solution. Okay. These aren't so bad, are they? So let's look at the next on a set of examples, and then I will release you to do some homework. That's the fun stuff. All right, so now we're solving this inequality. 12 is less than or equal to negative 4x plus 4 less than or equal to 48. Okay, so the first step is to simplify each side of the inequality separately. Well, looks like it's been done. We can't really simplify each side. And notice we have multiple less than or equal to's. All right, so now we need to isolate the variable. Well, what you do to one side, you must do to all sides. So if we're going to take out 4 from this side, we take out 4 from all sides. And that's include because we have inequality here and an inequality here. We got to do it to all sides. Now, okay, so this gives us what? 8 less than or equal to negative 4x less than or equal to 44. Now, we need to isolate the x, so this is multiplication. Notice this is a negative sign. Let's divide the negative 4 on all sides. Now, what happens to the inequality when we divide by negative 4? It gets reversed on both sides. So now we're left with this 8. Yeah, we're left with this. Well, this is negative 2 greater than or equal to x, because we isolated it, greater than or equal to negative 11. Now, we can't, we can, but we shouldn't do this when it's out of order. What I mean by out of order, negative 2 is greater than negative 11. See, we've always had the smallest number on the left-hand side. So what we can do to change this is rewrite this as the smallest number here, less than or equal to x, less than or equal to negative 2. So the biggest number. Okay. And this step is something that you can just logically think about. There's no math involved. You just needed to move the least number here to this side, and in doing so, it does flip the inequalities again. Now we can work on this. Let's graph it. So, in looking at this, let me just get out. That'll be good. Okay. And we're graphing it to get our intervals. Our intervals should be, well, we know we have a negative 11. Well, I don't have negative 11 on this thing. Huh. Well, let's draw a negative 11, maybe? Well, okay. But I do have a negative 2, so we'll draw a one of these line break thingies. Hopefully you've seen those, and it has a little break, and we have a negative 11. So let's write a negative 11. But this negative 11 is a closed. See, it's less than or equal to. It's closed. And then we'll write the negative 2, which is on a closed. Okay. So we have three notations because of this. I'm going to erase some of this because I need this space. We have three notations because it's a complex inequality. The first one is this line here. We also have a line here, but there's also this space in between. So for this is negative infinity, and this is negative 11, but it's inclusive. Remember that bracket? For this line in the middle, it's inclusive both ways because we see we have a dot on both ends, a closed dot, and it starts at negative 11 and it goes to negative 2. And on this one, we have a closed dot symbol up to infinity. That's our three notations. There are for a complex inequality. Let's test those three. So let's set it up like we have for the non-complex. It's exactly the same. Then we have the negative 11, the negative 2, and then the negative 2 to infinity. Draw our lines. Now we need test points. Well, our graph also helps us with test points. For this one, we would find a test point that is something beyond the negative 11 or less than, because we're going to negative infinity. So on this graph, it would be negative. Oh boy. Let me just make this a little cleaner. I'm going to have to start making more space. It would be negative 12. So if we're going on this graph this way, our next number is negative 12. Okay, let's go ahead and pick our numbers. Negative 11 to negative 2. So we basically just find a number in here. It can be the next number. So let's pick the smallest number that's not a critical number. So the smallest number is negative. I mean, the not smallest, but the easiest number to work with, it's not a critical number, is this negative 3 because it's the next number right here. These negative 2 going to infinity. The next number logically is negative 1, or we could try 0. 0 is always an easy one to work with. So that's what I'll try. All right. So for this one, we would write 12 less than or equal to negative 4 times negative 12 less than or equal to, oh, what was that? 48? It was 48, yeah. All right. So negative 4 times 12 is actually going to be a positive number. 12 times 4 is 48. So is 12 is less than, so this is going to be, it's going to be 48. Is 48 less than or equal to 48? Well, yeah, I think it might be. But did I do my math correctly? Because it seems like I'm missing something. All right, yeah, you know what? I am missing something. Let's redo this. This is fun stuff. I forgot. Because I had to erase the original equation to make the room, I forgot that original equation. it was actually negative 4x. Well, x is negative 12 now, plus 4. So instead of being 48, it will be 52. Now, is 52 less than or equal to 48? No. This is no solution. This one, we'll write it as 12. Well, you know what? Let's do it this way. Maybe 12 less than or equal to negative 4 times negative 3 plus 4 less than or equal to 48. Now, negative 3 times negative 4. So what's 4 times 3? All right, so it is 12. And we're adding 4 to it. And that is 16. Now, is 12 less than or equal to 16? Yes. Is 16 less than or equal to 48? Yes. So this is a solution. Let's try our handy 0 here. 12 less than negative 40 plus 4 less than or equal to 48. So 0 would turn into nothing. So you're just left with 4. So it would look like this. Now, is that true? Is 12 less than 4? No. So it is a no. So the only solution that we found was this right here. And we can graph that using our little graphing thing and our extension with our break in it at a negative 11. We will graph it using solid dot and this solid dot and making our line between them. No arrows on this line because it doesn't go off to infinity. Okay. Or I believe it's time to give you homework. Yep. So for your homework, let's do 1 through 30 blue. So chapter 2.2, 1 through 30 blue. All right, and good luck.